So, good morning, everyone, and welcome to the ISQG YouTube channel. My name is Davide De Biasio, and I am a member of the Outreach Activity team. Today, I have the pleasure of interviewing Dr. Flaminia Giacomini. Thank you very much for having accepted our invitation.
Thank you very much for inviting me. It's very nice to be here.
Thank you, thank you. So, Dr. Giacomini is a senior researcher in Zurich and a visiting postdoctoral fellow at the Perimeter Institute, working mainly on quantum gravity, but also on quantum reference frames and so on. Now, instead of doing it myself, may I ask you to please tell us something more about your research interests so I can make no mistake?
Yes, of course. So my research actually doesn't fit in what is traditionally considered to be quantum gravity because it has a different approach because it uses quantum information tools, but it addresses the same conceptual questions that arise in many quantum gravity approaches, typically in a different regime to the full quantum gravity regime. And so in particular, I'm interested in general in the conceptual questions that arise when we need to abandon a classical notion of space-time because we want to consider quantum effects in gravity. And the typical regime that I address is what is sometimes called gravitational quantum systems, which is quantum systems that are in some quantum state, for instance, in a quantum superposition state, meaning that they are at once here and there, and they source a gravitational field. So that's more or less the conceptual framework in which I'm moving.
So the idea behind this is that, and correct me if I'm wrong, for instance, you have a point particle that should source some kind of gravitational field. If that particle is not localized in space, you should start seeing something, at least at a quantum level. I don't know what kind of effect.
Yes. So if we think about Einstein's equations that are the basic equations of general relativity that connect the space-time with the source of the space-time. So for instance, the Earth sources a gravitational field. So, and the space-time that is sourced by the Earth, we know how to write it. It's like, and we have a formula for that that we can calculate through the Einstein's equations. So now these equations always consider a classical source. The Earth is a classical object for us. But fundamentally, we know that matter is quantum. So in principle, there is nothing that stops us from saying, well, if I have a particle here in my laboratory, a quantum particle, then why shouldn't this source a gravitational field? It's something that we cannot measure now because it's something that is very, very small. But in principle, there is no law in physics that tells us that this is impossible. And so we can ask what happens if inside the Einstein's equation, we want to put a quantum object. And then that's not something that we can solve anymore with classical Einstein's equations. And so we need to generalize the theory to do something more. And in particular, if we have something quantum on the right-hand side of our equations, we also need to, so on the matter side, we also need to have something quantum unless we really are ready to drastically modify the theory. And this means some sort of quantum generalization of our classical notion of space-time.
Well, in this sense, most of our viewers surely know that when you go from classical to quantum physics, you do not really use the same mathematical objects. So in this sense, it's really what you're meaning, right? That if you take these objects which are classical, you substitute a quantum one on one side of the equation, you need to equate it to some other quantum mathematical object, right? This is the main idea.
Exactly. Because otherwise it's inconsistent mathematically.
Sure. Well,
we can try to make it consistent by coupling something classical and something quantum, but that requires a modification to the theory. Yes. So we can also choose that road, but it's a different road. And
yeah, sure.
We wouldn't be talking about quantum gravity in that case, let's say.
Yes, sure. That might be, let's not express personal opinions on that, but in a sense, it seems to be hinted that really some drastic modification is needed in this sense, right?
Yes.
Let's start from some concept you've been working on, right, for quite some time, which is the one related to reference systems. And in order to start getting there, people usually take reference systems for granted, right? You learn that stuff in your first physics exam, then you bring it up again in your special relativity class, and then you drop it and take it for granted. So may we start by defining what a reference system is at a classical or relativistic level, and then slowly move towards the quantum version of that concept.
Sure. So in physics, usually we take reference systems as idealizations. So in particular, we can consider a reference system to be a choice of axes. So like we can choose an X direction, a Y direction, a Z direction in space, and the state of motion. So for instance, we will have, if we have a car passing by in the street, we will have a reference frame that is associated to this car. And so if I stand in the car, I look at the objects around me and I can describe them in that reference frame. But typically, I never really consider the car as my reference frame. It's idealize the car. I imagine this set of coordinates that moves with the car, and then that is the reference frame that I consider. But actually there is, if you really think about that, if I have a car that moves, then this car is a physical system, right? And more in general, I can, if I want also, if I want to measure a distance, what do? I take a ruler that is also a physical system. I put the ruler on the edge of a table, for instance, and I want to measure the distance between this table and another object. And then I count how many ticks of the ruler there are until the other object, and then I know what I've done. I know this is my measurement procedure. So basically, it's true that it is a very convenient idealization. But if we think in more operational terms, then we need to replace this idealization with a more physical notion of a reference frame as a physical system. So with that, there are different things that we can mean with this, but for now, let's just stick to the just general idea that somehow we want to relate the concept of a reference frame to a physical system. And then again, the laws of physics tell us that physical systems are ultimately quantum systems. And that's at the moment, it's our fundamental description of matter is quantum physics. So we might want to move to associating a reference frame to a physical system.
So if I may jump in just to try to pick up and see if I understood correctly, what you're saying is that before moving to quantum reference frames, what you're saying is that, sure, we use these axes and these idealized notions of distances and time lapses and so on and so forth, but those idealizations should in principle be dropped, in a sense that in the end, what you're actually doing is comparing to physical systems, namely, you said a ruler, a clock with some phenomenon or something like that, right?
Yes.
And since this is actually what we're doing, which was idealized at a classical level, we cannot neglect the fact that rulers, clocks, and stuff like that are subject to all those weird properties we find in quantum mechanics. Is this more or less the idea?
Yes, exactly, yeah.
Okay.
That's it.
And how do you proceed in that direction? So once you get this intuition, which I think is very clear, and I thank you for having explained it in such a clear way, where do you go?
So, okay, the stage at which we are now is to, okay, if you want, you can put an abstract coordinate system on top of a quantum system. So that's the status at which we are. So we're still missing an additional step, that is what happens if I actually want to build a reference frame using physical systems. But already this first step, like, how can I say? brought some interesting effects to us. So for instance, imagine that I have a quantum particle that is in a quantum superposition of being in two different positions. So it's in this position and this position at once. Now, usually, I always describe this situation from the perspective of some laboratory that is classical as far as we know. So imagine that I am here and I look at this particle from my reference frame. But now, imagine that I want to center my coordinate system. So now I'm really talking about an abstract coordinate system that I want to center in this particle that is in a quantum superposition of positions. What would I see? And what we found is that if you really center the coordinate system here, then this particle would see me in a quantum superposition state. And so basically this notion of what is classical and what is quantum is really something that depends on our perspective, and it's not really something that is given a priori. So basically this hints to the fact that everything is quantum.
So in a sense here, sorry if I stop you, but the idea is that your particle is in, for instance, this simple superposition of two positions actually, and you might imagine two reference frames, meaning really the axis and so on and so forth, and thus something which for us is classical actually has two superposed positions in the two reference frames. Is this more or less the idea?
Yes, exactly. Yes, it's exactly that.
Okay.
Yeah.
Wow. Okay, and this is simply at the level of attaching coordinate systems to quantum objects, right?
Yes, correct. Yes.
Okay. And where do you go from here? Like, once you've observed this, there's a lot of questions that come to my mind. For instance, what about rods? What about clocks? What about measurements and so on and so forth? So I don't know what you'd like to start, but
yes. So maybe something that is more related to gravity, since this is where where we want to go. I'm just thinking how to say it best.
Don't worry.
Okay. So now in physics, we have usually, so there is a notion of how I can mathematically formulate the change of a reference frame. Mm-hmm. So, and we know how that works. And we know there's a very important principle in physics that tells us that all reference frames are equal for the description of physics. So I can pick any reference frame and I should be able to do my calculation and to obtain the correct, say, outcome of a measurement in every reference frame. But now, if we have additional reference frames, this also means that I have to enlarge the set of transformations to reference frames. And this has important consequences because, first of all, it gives us a different symmetry principle for physics. And also, by generalizing the set of all possible transformations, we have some sort of quantum transformations, so quantum reference frame transformations, that if we do not have a classical notion of spacetime anymore, that's something that in any case we need to have. So at this point, the idea is to study that initially in a simpler system that is just a quantum mechanical system that is very, it's not wild. So we can control it very well. And then to try to make our way up towards more complicated situation where spacetime is actually not classical anymore for more fundamental reasons. Because, for instance, gravity is in a quantum state. So that's the idea.
Just to make it clear, so at a classical level, when you move from one reference frame to the other, you can either really stick to classical physics and use Galilean transformations, or move to special relativity at this stage, right? And use Lorentz transformations and boosts and so on. So what are you exactly referring to in this context?
Yes, so for instance, the Galilean transformations are something that is very well defined. And in particular, they have the property that if I apply one transformation and then another, this can also be written as a transformation, as a Galilean transformation, also the final one. And in principle, it's not clear that the same would happen if one extends these transformations to quantum reference frame transformations. But actually, indeed, we found that this is the case. So you can apply two of them consecutively, and also the resulting one is still one allowed transformation.
Okay.
So for experts, this means that they form a group.
That would have been the follow-up question, right?
Yeah.
So certified, still a group at a quantum level.
Yes, yes.
So, and this group allows you to go from superpositions of reference frames to superpositions of reference frames and so on.
Yes.
So, wow, this is super interesting, actually. But now, my natural question, going back to my starting point, is whether this also applies to a special relativistic context. Like, did you try to apply it?
This is something that we don't know yet.
Okay, okay.
Because the special relativity, so for one of the problems when you go to special relativity is that the notion of particle is a bit shaky. And then, okay, there are ways in which you can restrict to, say, the single particle regime and say, well, I can apply quantum reference frame transformation even there, but to like more fundamentally, then you would really need to go to a field picture. And that has an additional level of complexity. So we have some results in the relativistic regime at the particle level, but the field picture, we still, I mean, that's one of the goals. That's one of the directions where we are going. And it would be interesting to develop this more complete picture, but we still like work in progress, say.
That's the soul of research, right? Being
Yes.
in a constant work in progress. So that's completely natural, I guess. But is this, as you mentioned at the very beginning, you typically apply quantum information techniques to set problems. Is this, for instance, the case, like even at the Galilean level? Do you apply quantum information techniques to get these results? Can you please tell us something about it?
So in this formulation, what we took from quantum information is more like the operational approach. So there are many formulations of the operational approach. Here we consider that in a looser sense. So in the sense that basically all the equations that we write, all the elements of the theory correspond to laboratory operation. And that is because typically what you do in quantum information, so a standard thing that you do in quantum information is that you do not really want to trust your theory, but you want to trust, so you have different level of trust for your devices, and you want to trust the outcome of measurements that you obtain in the lab. And so you, basically the probabilities have a very important status, and you want to be able to, say, write as little as possible at the ontological level of something that you just have to postulate, but it is not needed in order to get observations. Of course, this doesn't mean that you never do it, you do it, because sometimes it's impossible not to do it. But the priority is given to what can be observed. And this is something that we are still keeping when we do this quantum reference frame formally. So when we set up this quantum reference frame formalism.
So you're saying that in the spirit of quantum information, you try to phrase everything in terms of things that can be touched, measured, done,
yes.
Operations and empirical observations. That's more or less the idea behind it.
Yes.
So, and now at this stage, just to make it clear, we are still at the level of idealized reference frames attached to quantum systems, right? And what about the next step? Because I guess that the natural thing would be to try to get rid of the idealized system, which is some which is part of your ontology, but in a sense, you don't really actually see some axes going around and being superimposed and so on and so forth. So how do you try to achieve this? Is this part of, first of all, of your research endeavor, and how do you go in that direction?
So at the moment, I'm not directly working on that, but there are other I'm stealing an office. So it's not really, so at the moment, this is not really part of what I'm working on directly, but there are some results already in the literature, more in the quantum information community, and these are also old results from, say, the 70s. So there is a very nice coincidence that the term quantum reference frame or related, so the idea of quantum reference frames appeared for the first time in the literature in quantum gravity and quantum information in the same year, that is 1967.
Okay. And
then the two directions went very differently. So the research that people have done on this in the two fields was very different for a long time. And the quantum information literature was focusing on something that is related to really associating a reference frame to really a quantum system. And that is done more in the sense of resource theories, it's called. So for instance, the fact that if I have a small spin, then this spin cannot tell me that this is the Z direction with very good precision. I will have a pretty bad information about what my Z direction is, because I only have a small spin. But if I put many spins one after the other, then I can define the direction much more precisely, because I have a more powerful system to tell me that this is the Z direction. And that, so basically, then to go into really associating a reference frame to a real physical system, then we would have to match somehow these two approaches.
So in a sense here, you're telling me, first of all, that in order to construct functioning reference frames, you need more degrees of freedom. Like you increase the number of degrees of freedom, you get a better reference frame. Is this more or less the...
Yes, yes. A quantum reference frame in a way is a bad reference, like a quantum reference frame in this sense is a bad reference frame, because like a small system cannot define direction very precisely.
But we expect everything to fluctuate and be superimposed.
Exactly. It's very quantum also, the direction that it defines. So yeah, and so one would have to try to combine these two approaches in order to have these two things. But in principle, that's something that people have studied for quite long. So we are not starting from zero.
Sure. So you're trying to merge results coming from independent communities that have worked more or less on similar intuitions that can be helpful in both directions. And this is always extremely fruitful and behind many of the great revolutions in physics. So this is one of the good approaches, right, in trying to discovering that different people have been working on the same problem without knowing it, right?
Yeah. It would be very nice too if we were able to do that.
Concerning the kind of picture you have in mind, just to try to make it clear, not only for myself, I made my interest evident, but also for everyone watching us, like bachelor students and master students and so on. What do you expect in the end when you have a quantum system, a real quantum physical realization of a reference frame? What you expect is more or less some correlators between observables concerning observables related to the reference frame and the object you're studying, something like that. You know, the spin, like you correlate the spin of the atom you're using as a reference for a quantum reference frame to some properties, some direction of motion of some quantum particle, something like that. Is this more or less the idea?
Yes, exactly. So maybe I can introduce an additional element that is a relational aspect in this formulation. And that goes very much in spirit with many approaches to quantum gravity and also with relativity, for instance. And the idea is that actually the physical things, whatever we observe, it's not something that is absolute, because in this case, we would have to get us out of the picture and be have a super status somehow. But if we think that we are actually part of physics, then what we observe are relations between things. So in this sense, I don't know, I can consider this spin to be the up direction, another particle that is pointing somewhere else, and then what matters is the relative angle between these particles. Or I have one particle here and one particle here, but if I'm one of these parts, so if I only have these two particles in the world, the only thing that matters is their distance. So everything would be phrased in terms of relations. And when I write down on a piece of paper the state of some system, then it's more the relation between my reference frame and this quantum system. It's not something that I can specify if I've not specified where I'm looking from. And
so just to make, just to boil it down maybe to layman's terms, what you're saying, and please correct me if I'm mistaken, but what you're saying is that there's actually nothing special about reference frames. They are just physical systems, as we said from the beginning. And when you describe something in a reference frame, what you're actually doing is choosing a particular physical system to be your reference frame and expressing everything in relational terms with respect to that. But you could have chosen the other. And like, for instance, velocities, right? Velocities are well understood as relational properties. What you somehow are saying is that in this relational interpretation, so approaches to quantum mechanics, everything should be like velocities, in a sense, like each observable should be relational, right? This is more or less.
Yes, exactly, yeah. And the relevant ones are those that are relational, yes.
Okay, wow, this would be groundbreaking in a sense, because quantum mechanics, in its classical textbook formulation, gives this importance to observers and measurements and so on and so forth. So it's quite natural for me, and you're free to tell me that this still has to be, this is yet to be understood, right? But how do observers and measurements and collapses of the wave function and so on and so forth fit into this picture, if they do fit at all at this stage, right?
Exactly. No, that's a very good question. So the short answer is that we don't know yet, but we tried to think about it a little bit. And it is not obvious. So at the moment, the best we can say is that if I have, so in quantum theory, there is a measurement problem, and there are various instances of this measurement problem, and roughly, it's very hard to define what it is, but roughly it's the idea that, well, I still have some deterministic dynamics of the theory, because the dynamics is deterministic, then the measurement is probabilistic, and then we have a discontinuity in the state, in the quantum state, that evolves when I apply a measurement. And maybe there is an instance of this measurement problem that is a thought experiment that was introduced by Wigner in 1939, and this Wigner's friend thought experiment, it's called, that gives a very nice intuitive picture of what is happening. And typically, so you have Wigner and the friend can measure some physical system. And then when the friend measures, this system is up, so the friend's knowledge of the system is updated, and then it either sees, I don't know, spin up or spin down, and so they record a measurement that is either spin up or spin down. But now imagine that the friend and the system are isolated, so Wigner cannot see what the friend is doing. And then he imagines that the friend might have done a measurement, but he doesn't know what the outcome of this measurement has been. And so he will describe the system, friend plus system, as a more complicated state that we call an entangled state, where that is basically a quantum superposition of the friend seeing up and the spin being up, and the friend seeing down, and the spin being down. And so now Wigner can now imagine to make a hypothetical measurement on both of them. And if he prepares the state of his measurement such that it's exactly the state that he thought it was, then he will find that outcome for sure with probability 1. But then we would have a difference in the probabilities that Wigner and the friend measure. And that is something that we don't have in any other situation in quantum physics. So that's strange.
And in this sense, if I'm not mistaken, this can scale up, right? Because I can myself make a measurement on Wigner, and you can do it to me, and so on and so forth. I think get more. I guess that in a paper by Sidney Coleman, Quantum Mechanics in Your Face, he described this feeling when he first learned about measurements in quantum mechanics, and this question about why we do not get superimposed when we interact with, we do not perceive being superimposed, at least when we quantum systems. And how does this measurement problem get framed within your perspective?
Yes, so, okay, maybe I made it a bit too long, but so now if we can imagine that, so now the friend for Wigner is something that is in a quantum superposition state. So it's like a quantum reference frame, basically. And so that's why I needed and so now we can imagine to phrase this situation also with quantum reference frames. And we were hoping that this relational approach would help us, but so far it hasn't. So we still have the same problem. And so we get out of this problem only if Wigner and the friend can talk to each other, and they can say which outcome the friend has recorded, for instance. And then we wouldn't, so basically we have to get out of this Wigner's friend-like situation in order not to incur into the measurement problem. So far, we haven't had really we haven't made a lot of progress on this, but we're not giving up. So maybe there is still something that, at least like that was the easiest try we could have done, and it didn't work. And then we can think about what happens if we get a bit more sophisticated.
But this, I think this is also important, and thank you for this, because many students are following us now. So to learn that advances in physics, in science in general, are often made by showing that the simplest possible approach doesn't work, and then trying increasingly complex approaches. And that's really important. So to stress this point, right? And okay, but when you say, just to make it a bit clearer, when you say that the two have to communicate, do you mean they need to have some kind of classical channel to talk to each other? Or is this still a purely quantum thing?
No, it can be also a classical channel. It doesn't need to be quantum. So they can also just send a piece of paper to the other one saying, I measured outcome up.
Okay, that's it. Nothing more than that. Yeah. Okay. But in this sense, like in this big picture you proposed us in this discussion and so on and so forth, we mentioned gravity, but left it to the side a bit, right? We mentioned it in our examples, in our attempts and so on. But we know that within the context of general relativistic gravity, reference frames are related by this wider and more general set of transformations, right? We typically call this general covariance in a very loose way. So can you tell us something about general covariance first and how it fits in this picture? But if it, once more, if it does, or if it, what have you done in this sense, and what can be done in the future?
Yeah, so general covariance is basically a generalization to general relativity of the idea that I was mentioning before, that we can basically take any set of reference frame and the laws of physics hold in this frame. So general covariance is the more sophisticated version of that. When you have general relativity, that is so it's also the mathematical formulation of it is also a bit different to the one that we have just in like standard classical physics. And so what I would like to have, but I don't know whether, like, so again, this is all yet to be done. What I would like to see is that some form of general covariance also works in a wider class of frames that are quantum reference frames. So what I would like to set up is a formulation that shows that this is not true. Like the idea of general covariance is not only true for classical reference frames, but also for quantum reference frames. And I mean, I have some ideas on how to proceed, but that's at a very preliminary stage at the moment. So,
in this sense,
but it would involve, again, generalizing the group of transformations of general relativity to quantum. So the group of transformation of general is the diffeomorphism group for experts again, and this would be a quantum version of these diffeomorphism transformations.
So that would have been my question. So you expect to extend diffeomorphisms in the same sense that you extended the Galilean transformations before?
Yes, exactly, yes.
And this is the picture within which clocks and rulers can be seen as actual quantum systems for quantum reference frames. Is that correct?
Yes, that's correct.
Okay.
Yes.
Okay.
Yes.
So,
I mean, with clocks, one can think about also easier situations. Because I mean, we don't need full general relativity. We can just put them. So we can use a couple of tricks. One is so we know, and this has been measured, that in the gravitational field of the Earth, according to the height of a particle, the clocks tick differently. So, for instance, a clock that is here ticks more slowly than a clock that is up here. And this is an effect that is called gravitational time dilation. And so it's just because they are in the gravitational field of the Earth, and then the stronger the gravitational field is, so here, the more it slows clocks down. And this has been measured by an experiment couple of years ago, up to the level of the millimeter. So the clocks that are distant, just 1 millimeter apart, tick differently because of the gravitational field of the Earth. And so we know that we know this experimentally, we know that very well. Not well enough for what is needed to put it with quantum, but still very well. And so now we can imagine a clock that is in a quantum superposition of positions in the gravitational field of the Earth. And then it ticks in a quantum superposition of times, basically. And so we can think about effects due to the fact that also the clock is a quantum system, and a clock being a quantum system is something that it's easy. Like people can do it already nowadays in the lab. It's just a particle, like an atom, that has some internal energy levels, and these internal energy levels act as a clock. So it's very
kind
easy.
of fluctuates between the two in some periodic fashion. Okay.
Exactly. And so now we can come up with thought experiments about that. And also the other thing that I think is nice to think about for the clocks is, so we know that E is equal mc squared. And that's, I think, an equation that everybody has seen at some point.
On some mug, on some postcard.
But this means that mass and energy are basically two aspects of the same thing. And so if I have a clock that has some internal energy levels, and I use these energy levels to measure time, this internal energy also contributes to the mass. But now these internal energy levels are in a quantum superposition. And this means effectively that the mass is also in a quantum superposition. So, of course, this is a super small effect, but at least conceptually, it it tells us where we have to go in terms of thinking. Because if the mass is in a quantum superposition, then already this is not inside Einstein's equations. As we mentioned previously, these are just classical, and if the mass is itself a quantum variable, then again, we are out of the scope of general relativity.
And in some sense, you need to go beyond towards actual quantum gravity.
Exactly.
This whole business of getting rid of a classical notion of reference frame really is like takes some ground off your feet, right? It takes you, removes that kind of thing you hook yourself to when trying to dive deep into quantum gravity. So it really feels, whenever you look, more things, more effects pop out. And this is not only extremely interesting, but appears to be really hard to conceptualize. So, and okay, like from this point, which is some more personal thing, and I'm extremely sad that we have some time constraint, but I'd like to move to a final question, which is a kind of surprise question, a bit more personal on your side, if you may. So if I can ask that, otherwise we'll cut the interview and get rid of it. But why did you choose to work in these topics? I think that an answer to this question can be helpful for students, bachelor's, master's, and so on. So why these topics and not, for instance, condensed matter or particle physics or medical physics and so on?
So what drives me and what I was always curious about are really fundamental questions. So like asking the big questions in physics, and like understanding space, time. Already like even before I studied physics, this was like getting to know the laws of nature was really what I was curious about. Yeah, and I also like very much conceptual questions. So I didn't know until I had to choose whether I would like to do physics, philosophy, or maths. And then I chose physics because it felt it was a bit in between the two. I could do a bit of both. And so, yeah, to me, really like the conceptual questions were interesting, and the problem of quantum gravity, of having these two theories that work very well, but that we cannot put together, was extremely fascinating for me. But also, I like to think about something that I can picture in my head. So I wanted to do something that where I could imagine the physical system that is like that I'm studying, where maybe I would even be closer to experiments. So I'm talking to experimentalists now. And so I found that, so it is sort of a bit of a niche field, but it's where I felt more comfortable because of my mindset and because of my interest. And so so basically the reason is really that I like this small bubble that I have, and to think in these terms, and then connect it to other fields. That's also something that is very nice for me, because it's a field that is very easy to connect to other disciplines, because you can talk to experimentalists, you can talk to quantum gravity, like to real quantum gravity researchers, not like fake quantum gravity researchers like me, and to researchers in quantum information. So there are many connections with other fields. And that's also something that I like, because then you can learn a lot from other approaches and try to see what you can import in your research. So and there's space for development because it's new. So it's a new field, and so there's a lot of space for making it evolve in different directions.
It's somehow thrilling, right, to be part of a new research project.
Yeah.
I think that your answer was more than satisfying. So I thank you again for having been here, for having accepted our invitation. I'm sure this whole interview, I mean, your contributions will be extremely valuable for all our viewers, not only for for me. And thank you again, really. This was...
Thank you very much.